At the end of this session, you will be able to describe the physical meaning of Maxwell's equations, perform calculations involving electromagnetic plane waves, explain the concepts of Poynting vector, intensity, etc., how energy is computed for electromagnetic wave and photon, describe how electromagnetic waves possess momentum and can cause radiation pressure, and finally discuss practical applications of electromagnetic waves and be familiar with electromagnetic spectrum. So far, all the theories or all the equations, all the phenomena in electromagnetism can be explained using 5 equations, and 4 of these equations pertain to Maxwell equations. All equations in mechanics can be derived from Newton's laws or Newton's 3 laws of motion. The counterpart of that is Maxwell's equations when it comes to electromagnetism. You're already familiar with Gauss's law, and you were introduced with Gauss's law in terms of the integral equation E dotted to dA is equal to the charge enclosed E and C over epsilon naught, or the permittivity of free space. So this equation describes the relationship between a charged body and the electric field it produces. So that's why ideally the circle in this integral sign means that you are integrating a closed surface, and A here is the area. Next, we don't have a specific symmetric counterpart when it comes to magnetism. We have this Gauss's law for magnetism. The integral of B dotted to dA is equal to 0. In other words, there's no such thing as magnetic monopole. We don't have a charged version for magnetism. In Gauss's law for electric fields, you have this concept of charge, and this charge generates electric field. However, we don't have a specific stationary or static quantity that generates magnetic field. That's why this is 0. Next, if you're done with watching my lecture on electromagnetic induction, then you are familiar with Faraday's law. Faraday's law, this is equal to the integral of E dotted to dl. Physically, what this means is that you're trying to calculate the electric fields at a specific path or landing on a specific path, and this path must be a closed path. And once you integrate that, you will have a non-zero value if you have a non-zero time derivative of magnetic flux. What this tells us is that a changing magnetic field produces an electric field that can be integrated along a closed loop. So finally, we have Ampere's law, but I'll directly write this as Ampere-Maxwell law because Maxwell added a correction to Ampere's law. Ampere-Maxwell's law. So initially, Ampere's law looks like this: B dotted to dl equals mu naught I. But notice that when it comes to Faraday's law, this line integral of electric field is equal to a time derivative of something. So that's what Maxwell is looking for. This line integral of B dotted to dl must also equal to a time derivative of something. So he added a correction factor, mu sub 0 times epsilon naught d phi over dt, wherein d phi sub E means you're looking for a electric flux. Maxwell added this correction factor to make the entire Maxwell's equation symmetric. So later I'll discuss something about this. So for now, just accept that there is a correction factor here. Ampere-Maxwell's law tells us that a changing electric field, this one, produces a magnetic field that can be integrated along a closed loop. Now, if you have a charged body, you can now predict its behavior when it is influenced by an electric field or magnetic field. You're able to predict its behavior by using Lorentz force equation, which is equal to the electromagnetic force acting on a body is equal to the influence of the electric field on that charged body plus the influence of the magnetic field, which is equal to QV cross B. Now, going back to this correction factor here, if you have a wire, let's assume that this extends to infinity and charges is flowing inside this wire. When charge moves this way, assuming that there's a constant current throughout this wire, so if I try to do a line integral here and calculate the line integral of the magnetic field along the circular path here, Ampere's law dictates that this is equal to mu sub 0 times I. What if we have a parallel plate here This is a metal plate and another metal plate. It's connected to a wire. So what if there's a sudden burst of current in this direction? For example, positive charge pushing another positive charge, and at a very quick instance, there is a sudden accumulation of positive charges here. This will generate an electric field. At a distance, without any transfer of charges, suddenly some of the positive charges here will be mobilized and then suddenly pushed on this side. So at a very quick instance, there is a sudden non-zero value of current in this region. So if I try to integrate or calculate a line integral in the middle, notice that there's no specific value of current here. So this must be equal to 0, but I was able to still push the other positive charges on this side without any physical charges moving in this region. So in a way, Maxwell decided that there should be a non-zero value here since there's almost continuity of current when there's a sudden burst of current on the other side. He called this current as displacement current because this current was able to displace the other charges on this side of the conductor. And he knew that this is possible because of an electric flux on the other side. We denote displacement current with I sub d, and Maxwell just decided that displacement current must be directly proportional to electric field. But since he's targeting for asymmetric form with Faraday's law, he just assumed that this must be directly proportional with d phi sub e over dt. In mathematics or in any physical sciences, when you have a relationship, for example, A directly proportional to B, this becomes equation when you perform some regression analysis, and this will become an equal sign when you have a factor called constant of proportionality between A and B. So what we're lacking here is a constant of proportionality. In order for this to become an equal sign, there must be a constant factor here. To get that, remember that the definition of current is dq over dt, or the time rate of change of physical charges moving past a given point. So I must replace this q in terms of flux, but this is actually equal to flux. So if I try to rearrange this, I'll have Q equals flux times epsilon naught. So plugging this here, I'll have I equals d over dt times epsilon naught over phi sub e. Epsilon naught is constant. I can bring this out of the time derivative operator, and then I'll end up with d phi sub e over dt. So now I can plug this back in the previous equation. Instead of writing directly as I sub d, I must copy this form to maintain the units on both sides. So mu sub naught times id, but recall that id is equal to d phi sub e over dt. The complete form of the Ampere-Maxwell equation. Now let's try to visualize electromagnetic waves and check its mathematical representation as a plane wave. Consider these x, y, z coordinates and assume that along this z-axis lies a conductor, for example, a metal rod. Now imagine we have a charge that is initially at the origin, and it oscillates back and forth along this z-axis. So because of this, it produces an electric field vector that also oscillates along the z-axis. So this electric field vector changes in magnitude over all space. In fact, you could picture this change in electric field in a radially symmetric form. In other words, the electric field varies over all space. However, to simplify our visualization, let's just look at electric field vectors that are perpendicular to the y-axis because it has the greatest variation of electric field as seen by this charge oscillating on this rod. And at the same time, this is true for the x-axis, but let's just focus on electric field propagating in the y direction for now. Now, because of this oscillation, notice that electric field vectors gradually changes from this direction to this direction, I mean along the z-axis. However, according to Maxwell's equation, a changing electric field generates a changing magnetic field or a time-varying magnetic field. Also, and a time-varying magnetic field produces an electric field. So we can also draw a time-varying electric field that is along the xy plane. Now, how do I know that these electric field vectors are perpendicular with respect to these electric field vectors? The answer is based on my discussion in electromagnetic induction. Maybe after this, you may want to review it. To mathematically represent this variation in electric field along this direction, I can simply just draw a sinusoidal curve that coincides with this electric field vector. And from there, we try to develop wave equations that are consistent with Maxwell's equations. For example, I'll just draw a curve that matches the length of this electric field vectors. Let me draw this three-dimensional wave in terms of its projection along the ZY plane. So it's easier to visualize. So for example, this is the Z-axis and the Y-axis. Based on this figure, I can simply just draw this electric field vectors as a sinusoidal wave. Let's just assume that this is the amplitude of this electric field vector. So let me denote its amplitude as E sub 0. To mathematically describe this, recall that when you have any kind of wave, we denote its period with capital T, which is the time required for a complete oscillation. And the frequency is the number of complete oscillations per unit time, and it's just the reciprocal of 1 over capital T. Now, oftentimes when you have a repeating pattern, it's easier to analyze the system in terms of 2 pi or its value from 0 to 2 pi. Because of this, we can convert this spatial frequency into an angular frequency, which we denote as omega equals, since we would like to oscillate it along 2 pi, so we have a factor here, 2 pi. Now, another quantity used to study waves is a quantity called wave number, represented by K. Now, wave number is the number of wavelengths that can fit into the scale of 2 pi times whatever units we are using. So mathematically, we represent this as, again, the number of wavelengths that can fit into a scale of 2 pi times something. This is actually written as 2 pi over lambda. Going back to our figure, one equation for this is E equals, just for notation, let me put a subscript Z here to remind me that this is an electric field that oscillates along the Z-axis. Recall that in our example, there's actually a fluctuation of electric field in all directions. So it's not just along the Z-axis, but for our purposes, let's just focus on the oscillation of electric field along the Z-axis. And this is equal to, remember that any kind of wave must have an amplitude, so E sub 0 times, the best way to describe this kind of curve is a sine function or a cosine function. Let's just represent this as sine, and the dependent variable is y, so sine of y. Now, if this curve is moving along the y direction, then the set of points in this argument must move in such a way it represents the velocity of the wave. Hence, I can write this as E sub zy equals E sub 0 sine of y plus or minus the displacement of the point. If you just try to plug any numerical value here in this position, notice that if that value is positive, you are letting this wave move in this direction. You could just play around with any kind of numerical value. If we have a wave with a velocity v, then I can replace the displacement here with, let me just assume that the wave is moving in the positive y direction. So I'm going to use y minus. Let's assume that if the wave has a velocity v, recall that velocity is equal to displacement over time. So I'll just write displacement over time. So I can replace this displacement here with v times time. So that's it. So our equation is beginning to take shape. Finally, my goal here is to convert everything in terms of a quantity that has something to do with an angular value. Because normally when you have a trigonometric function like sine or cosine, its argument is an angle. So for example, sine theta or cosine theta. And notice that this argument is still in the spatial domain. So my goal here is to convert these spatial values into a quantity that has something to do with angular values or angle. In order to convert this spatial argument into an angular argument, we have this concept of wave number. And again, the wave number, K, is the number of wavelengths that fits into one complete cycle. And this numerator here, if I try to rewrite this in a more general way, has something to do with one complete cycle in angles. So if you try to observe this numerator here, it's in radians divided by the length of one complete cycle. So this denominator here is in spatial domain, so length of one complete cycle. So in order to convert this spatial argument into angles, I'll just multiply this entire term with k. So I now have e sub z of y equals e sub 0 times sine. I'll multiply the entire term with k so that I can convert this spatial argument in terms of angular argument, k times y minus vt. So I'll try to distribute this. I'll have e sub 0 sine ky minus kvt. However, note that velocity of a wave is equal to wavelength over period, which is also equal to lambda times frequency. So because the reciprocal of period is frequency, and I can plug our expression for angular frequency here. So V equals lambda times omega over 2 pi. So I'll end up with V equals omega over k, since 2 pi over lambda is equal to wave number k. If I try to rewrite this as omega, so omega equals Vk. This term here, Vk, V times k is just omega. And this is our expression for the electric field component of an electromagnetic wave moving along the y direction. And from our figure above, using the same reasoning, since our magnetic field is oscillating along the x-axis, let me just put a subscript x here. By the way, they are now both function of displacement and time. E here is supposed to be a function of displacement and time, and also this magnetic field curve expression is equal to b sub 0 sine ky minus omega t. So this is our expression for magnetic field component oscillating along the x-axis of an electromagnetic wave moving along the y direction. So going back to this figure, notice that if I randomly position a plane parallel to xz plane, for example, and draw another plane exactly one wavelength from this plane, notice that this plane has the same magnitude of electric field. The equation we just derived, this one, is a representation of plane waves. And through this simplification, we can analyze other properties of electromagnetic wave as long as the variables in the plane wave equations are consistent with Maxwell's equation. Going back to this Maxwell's equation, this 4 equation, in higher physics, you can convert each of these equations in terms of del operator. Then once you convert all of this equation, you can use the backup rule of vector operations. And you will be able to derive the wave equation. And from the wave equation, you will have this expression, C equals 1 over square root of epsilon naught mu naught. Here's a surprising result. C is the speed of light. And it's actually derivable from two constants, permittivity of free space and permeability of free space. And this connection between the speed of light and the constants associated with the electric field and magnetic field tells us that light is one example of electromagnetic wave. In a way, this is a mathematical statement that light is one example of electromagnetic wave. This problem is from OpenStack's University Physics Volume 2, Plane Electromagnetic Waves, Problem 41. If the sun suddenly turned off, we would not know it until its light stopped coming. How long would that be, given that the sun is 1.496 times 10 raised to 11 meters away? So when answering word problems like this, try to draw if you can draw the system. So here we have a sun, and this is the planet Earth. Let's represent the distance between the sun and the Earth as d. We are given with the distance between the sun and Earth, which is equal to d equals 1.496 times 10 raised to 11 meters. And we're looking for the time of travel of this light. We already established that light is an electromagnetic wave, and one thing that connects distance and time is velocity. And we already established that if an electromagnetic wave travels in vacuum, then it must have a value of c. Velocity is equal to distance over delta t, and we're looking for this value. So I'll rearrange this in terms of delta t, then I'll end up with delta t equals d over v, which is v is equals to celeritas, or the speed of light. Plugging in the values, I'll end up with 498.67 seconds or 499 seconds. Any kind of wave, not just electromagnetic wave, can carry energy from one point in space to another. In this case, the energy for an electromagnetic wave is carried by electric fields and magnetic fields. To quantitatively describe the energy carried by electromagnetic waves and at the same time describe the direction of electromagnetic wave, a physicist introduced a new vector, and this new vector is called Poynting vector. This is named after an English physicist named John Henry Poynting. It was introduced in 1884. We represent it with capital S. Poynting vector is equal to 1 over mu sub 0 E cross B. So from our figure, if we represent electric field, this electric field here with an amplitude, let's say E sub 0 times, it's along the z-axis, so it's z hat. And the magnetic field is, to make calculations easier, I'll put z here so that we are aware of the direction even if we drop this z hat here. We know that E sub z is the electric field component of this wave along the z-axis, and let b equals, it oscillates along the x-axis, it must have a component along the x-axis, and this is along x hat. So if I try to use this, I will be able to determine the direction of the electromagnetic wave. This is equal to S1 over mu naught. So E sub z, z hat, cross B sub x, x hat. When doing cross product, it's easier to write it this way, mu sub 0. So you have x hat, y hat, z hat, and then this first vector here has a z component, which is E sub z, and it doesn't have any non-zero component along x hat and y hat, so I'll just put 0 here. Then for this second vector, we have b sub x, because it has a component along the x hat, but it doesn't have any component along the y hat and z hat, so I'll just put 0 here. So when it comes to x hat, the first term is 0 minus 0 times z until it reaches z hat. So this is also 0. Plus, when it comes to y hat, E sub z times b sub x minus 0 times 0. So I'll have 0 plus, this is that term, so it's also 0, minus b sub x times 0 equals 0. So I'll end up with 1 over mu naught E sub z b sub x y hat. And notice that the structure of Poynting vector tells us that the resulting electromagnetic wave travels along the y-axis, and it's consistent with our figure. So let me just focus on its magnitudes. It's actually equal to energy of the electromagnetic wave that passes through a given area per unit time. Or in other words, this is actually energy divided by area is energy flux divided by time. So now recall that energy per unit time is also power. This is power, remember, in mechanics. The magnitude of the Poynting vector can also be regarded as power per unit area, and this, we have another term for this, which is intensity. Intensity is equal to power divided by area. In reality, our eyes and even the sensors in your camera, the smartphone cameras, do not actually calculate each individual electric field and magnetic field vector. What it does is that it output an average value or singular value of this time varying or flickering electromagnetic field vectors. In other words, our eyes and even your smartphone cameras just perform some averaging to represent a singular value of energy out of this varying or flickering energy. Now, I'm saying that the energy coming from electromagnetic wave is time varying because the electric field and magnetic field vectors are sinusoidal function of time. That's why by convention, when we say intensity, we're actually calculating for the time average of the Poynting vector magnitude over one complete cycle. So before we write intensity in terms of electric field amplitude or magnetic field amplitude, let's recall the concept of energy density because it will greatly simplify our expression. In my discussion of capacitance and inductance, we have this concept of energy density, which is represented by U. In order for this to become energy, since this is density, I need to multiply this with volume. Let's represent this volume with capital V. So if we have imaginary cylinder floating in space, if electromagnetic waves passes through this cylinder, I can calculate the volume of electromagnetic wave that passes through this imaginary cylinder as long as I can calculate its area here and this length of the cylinder. So area times length will give me the volume, but I would like to write this in terms of something that is intrinsic with electromagnetic waves. So I'm talking about the speed of light, and we call that the speed of light, assuming that the light travels from this point to this point at a time interval delta t, then C is equal to this length divided by delta t. This length can be rewritten as C delta t. So now I have expression for volume, which is also equal to area times C delta t. One definition of capacitance is that it's the ability of a conductor to store electric energy, and this energy is stored in the form of electric field. So we were able to derive the energy density of electric field based on the amplitude, and it was derived in our discussion of capacitance. So we have an expression for the energy density of electric field, which is equal to 1/2 times epsilon naught times the amplitude of electric field squared. Also, we were able to derive the energy density of magnetic field based on magnetic field amplitude, and it was derived in our discussion of inductance, 1 over 2 mu naught B sub 0 squared. So apparently, if I want to get the overall energy density, and when you have an electromagnetic wave, there exists an electric field vector and magnetic field vector. So the total energy density for an electromagnetic wave must be the sum of the two. So U sub E plus U sub B. Let's assume that the presence of the energy density of magnetic field is equal to the amount of the energy presence of this energy density U sub E. So we have this wild assumption that U sub E is equal to U sub B. So if I try to divide both sides, I'll end up with... Now this is a very wild assumption since electric field energy density and magnetic field energy density are not always equal, but this will greatly simplify our expressions later. So if I try to plug this here, and I'll end up with epsilon U sub 0 E sub 0 squared over B sub 0 squared equals 1. Recall that C equals 1 over square root of epsilon naught times mu sub naught. So this is actually equal to 1 over C squared. Epsilon naught squared equals, by the way, this is C squared, B sub 0 squared. So I now have a new relationship. If I try to get the square root of both sides, assuming that they do not involve complex numbers, this can be simply written as E sub 0 equals C times B sub 0. We now have a relationship between the electric field amplitude and the magnetic field amplitude of an electromagnetic wave traveling in free space. I can replace E sub 0 here with this, and at the same time, I'll have another expression for the total energy density, and I can rewrite this as B sub 0 equals E sub 0 over C, and then plug it here. I'll have another expression for the total energy density of the electromagnetic wave. So I'm not going to plug it here. I'll just write here the resulting equation. So another way to write the total energy density is epsilon naught E sub 0 squared And another way to write it in terms of magnetic field amplitude alone is E naught squared over mu sub 0. This problem is from OpenStack's University Physics Volume 2. It's about the chapter on the energy carried by electromagnetic waves. And it's problem 51 from that textbook. A radio station broadcast at a frequency of 760 kilohertz at a receiver some distance from the antenna. The maximum magnetic field of the electromagnetic wave detected is 2.15 times 10 raised negative 11 Tesla. The maximum magnetic field here is actually another term for the amplitude of the electromagnetic wave for the magnetic field vectors. I could just simply write this given as B sub 0 to denote the amplitude of the magnetic field for this EM wave, which is equal to 2.15 times 10 raised to negative 11 Tesla. Now, another given is this spatial frequency, F equals 760,000 hertz. In part A, what is the maximum electric field? We were able to derive a relationship between the magnetic field amplitude and the electric field amplitude just by assuming that there is an equal amount of electric field energy density and magnetic field energy density. We're looking for E sub 0 here in part A, and the equation that relates E sub 0 and the given is E sub 0 equals C times B sub 0. So plugging in the values, we have 3 times 10 raised to 8 meters per second times 2.15 times 10 raised to negative 11 Tesla. Plugging in the values using your scientific calculator, we have 6.45 times 10 raised to negative 3 volts per meter, or another unit of coulomb is newtons per coulomb. In part B, what is the wavelength of the electromagnetic wave? We have a given of frequency, and when electromagnetic wave passes through air or through vacuum, we can assume that it has a speed of c. C is equal to wavelength over period, and the reciprocal of period is frequency. We can now calculate for the wavelength. So wavelength is equal to c over f. And plugging in the values, I'll end up with lambda equals 394.74 meters. Let me return to this figure. The physical meaning of the magnitude of a Poynting vector is that it is the energy flux per unit time. This is energy flux, and this is per unit time, so times t. And notice that I can calculate energy by multiplying energy density with volume. And recall that we were able to derive a particular equation for volume that involves the speed of light and time, u times AC times time, or delta t, divided by A times time. So this cancels out, this cancels out. So another expression for the magnitude of the Poynting vector is S equals to U times C. We have several expressions for U. So U can be equal to epsilon naught E sub 0 squared, or U equals B sub 0 squared over mu sub 0. I can plug those two values here, and I'll now have another expression for S, which is S equals epsilon naught C E sub 0 squared. Now recall from previous discussion that S takes this form, 1 over mu naught, and this can be E sub Z, then B sub X, Y hat. But let me just write the amplitude as E sub 0 and B sub 0. Now, if I'd like to get the magnitude of this vector, then I'll just have to do this S dotted to the S hat, then take the square root. This is also equal to taking the dot product of the same quantity with itself. So I'll end up with 1 over mu sub 0, E sub 0, B sub 0 squared Y hat dotted to Y hat. And I'll end up with this magnitude of the Poynting vector. So now if you have a value for the electric field amplitude, and the magnetic field amplitude, then you can now calculate for the energy flux per unit time of an electromagnetic wave. Or the other way around, if you have a value for the energy flux per unit time of an electromagnetic wave and you're given with, let's say, amplitude of electric field, then you can calculate for the magnetic field amplitude. We would like to consider intensity. Recall that intensity is the time average of our pointing vector. This time, we would like to calculate the time average of our previous sinusoidal wave equation. So we'll have an equation for intensity. Our wave is represented by E sub 0 times sine ky minus omega t, and let theta equals ky minus omega t. We have E squared, this one. When we have this expression E sub 0 squared, it's like taking the square of this expression, but the time average of sine squared theta in calculus is just equal to 1/2. Since we already established from the previous discussion that intensity is just the average value for the magnitude of the pointing vector, then I'll just have to simply multiply this with 1/2 to get the magnitude of the intensity. So I'll have 1/2 epsilon naught c epsilon naught squared. We have another expression for you. This time I'm just going to write it directly here instead of looking for it in the previous artboard. So we have u equals b sub 0 squared over mu sub 0. And since S is equal to energy density times speed of light, then I can plug this here at U. So I'll end up with C b sub 0 squared over mu naught. Since this is an expression for S, recall that I can just multiply this S with 1/2. Then I have another expression for the intensity, which is in terms of magnetic field amplitude. So this is another expression for intensity that is in terms of magnetic field amplitude. There is another expression for intensity, which we will be deriving using this expression, and I'll just save you the time of deriving it. This is equal to I equals 1/2 times E sub 0 times B sub 0 over mu sub 0. So this time, let's discuss the momentum carried by electromagnetic waves and the resulting pressure that comes from this wave. So consider this electromagnetic wave represented by these plane waves instead of those fluctuating electromagnetic wave vectors. These plane waves is moving towards this surface, and this surface consists of material particles, and its atoms or molecules can contain ions or even just some excess electrons. The bottom line is when this electromagnetic wave lands on this surface, this EM wave can exert forces on these charges, and by virtue of Newton's second law, the existence of force is a result of a change in momentum or momentum transfer. If you try to recall the original form of Newton's second law, force is actually equal to a time derivative of momentum or a time rate of change of momentum. Just so happen that if you plug the definition of momentum here, mv, mass times velocity, and assume that mass is constant throughout the motion, we'll end up with mdv dt, which is ma. So ma is just another form of Newton's second law wherein you assume that mass is constant. When there is a force applied on this surface, there must be a change in momentum. Now, if this surface is a perfect absorber and this EM wave, let's assume that it carries a momentum P, then the momentum transferred to this surface is P, okay? Because we assume that it's a perfect absorber. On the other hand, if this surface is a perfect reflector, then the momentum transferred onto the surface has twice the magnitude of this electromagnetic wave, which is 2P. So you might be wondering why. If we try to explain this in an intuitive way, imagine this is the momentum exerted by the electromagnetic wave, and the photon bounced back, implying that the particle somewhat elastically restored its position. Momentarily, for example, this charge moved in this position and then momentarily returned to its position. So the change in momentum is equal to P minus, since this is negative, because the direction is reversed, this is negative p. So the change in momentum is 2p. If the momentum exerted is twice as great, then the force exerted is twice as great. For a perfect reflector, if you have a factor of 2 in the momentum because the momentum is twice as great, then the force exerted is also twice as great. So you have a factor 2 for the force exerted when you have a perfect reflector. When there's a force being applied on a surface, and this surface has a measurable area, we can describe this interaction in terms of pressure. Since there's a non-zero force and there's a non-zero area for this surface, then we have a non-zero pressure, and this is where radiation pressure comes in. From your mechanics class, we have another expression for power. So since I used P for pressure, let me just write the word power is equal to force times velocity. To write this pressure in terms of intensity, the general definition of intensity is power over area. It's a measure of the power delivered through a certain surface area. So let me rewrite this first into FV over area, and then I'll now have expression for force. So let me write this in terms of force. Force equals IA over velocity. Then plug this here. I can write radiation pressure in terms of IA over velocity times 1 over E. This cancels out. Here's my expression for radiation pressure. P equals I over the velocity of the electromagnetic wave. Now, if the electromagnetic wave propagates in vacuum, then this speed must be the fastest speed possible for an electromagnetic wave, which is c, or the speed of light. Therefore, for an electromagnetic wave traveling in vacuum, this is the expression for radiation pressure. Now, if the process involves a simple transfer of momentum, like in a perfect absorber, then this is our expression for pressure. However, if we have a perfect reflector, notice that we must have a factor 2 in force. So initially, if this is our expression for pressure, we must have a multiplier of 2 here. Just to save time, the expression for pressure, if you have a perfect reflector, is 2 times I over C, or twice the intensity of the electromagnetic wave divided by the speed of electromagnetic wave in vacuum. Electromagnetic waves are divided into 7 categories based on their wavelengths or frequency. And this entire range of various electromagnetic waves lined up is called electromagnetic spectrum. So for radio waves are electromagnetic waves with wavelengths greater than 10 centimeters. And radio waves are typically generated from broadcast antenna with alternating current. They have wide applications including AM and FM radio waves or radio communication and TV signals. So for microwaves are EM waves with frequencies that range from 10 raised to 8 hertz to 10 raised to 12 hertz. Now this is raised to 12 hertz. Common applications of microwaves include radar, of course, microwave oven, cell phone communication, Wi-Fi, Bluetooth, RFID, and so on. Now, infrared waves, the difference between infrared and microwaves is not well defined. A common application of IR waves is thermal imaging, and also sometimes this is used in remote controls. Visible light is an electromagnetic wave that ranges from 400 nanometers to 750 nanometers. Now, this is the electromagnetic wave obviously detected by the human eye. Next, ultraviolet radiation. Ultraviolet waves are EM waves with wavelength from 400 nanometers to 10 nanometers. UV waves coming from the sun are divided into three: UV-A, UV-B, UV-C. This division is based on their wavelength. This is from 320 nanometers to 400 nanometers. This is UVB is from 290 nanometers to 320 nanometers. And UV-C is 220 nanometers to 290 nanometers. Among this classification, UV-B causes vitamin D production. The rest, strong exposure to this leads to skin cancer. X-ray are electromagnetic waves with wavelengths from 10 raised to negative 8 meters to 10 raised to negative 12 meters. Apparently, the common use of X-ray is for imaging objects that are opaque to visible light, like our human bones. Finally, gamma rays, the strongest of all, electromagnetic wave that possess the most energy. Gamma rays results from nuclear decay. A common application of gamma ray is in nuclear medicine. This problem is from OpenStack's University Physics Volume 2, section about electromagnetic spectrum, problem 77. An outdoor Wi-Fi unit for a picnic area has a 100 milliwatts output and a range of about 30 meters. What output power would reduce its range to 12 meters for use with the same devices as before? Assume there are no obstacles in the way and that microwaves into the ground are simply absorbed, meaning to say they are not reflected. Let me draw the system. For example, this is our Wi-Fi that has a range of 30 meters. So for example, let's denote this range as R sub 1. So this is R sub 1 and it has a power output of 100 milliwatts. R sub 1 is equal to 30 meters. Now, it wasn't mentioned in the problem that EM wave or its amplitude will be changed when we reduce its range. Hence, the same microwave delivers the same intensity. But before that, let me draw the other case wherein we reduce its range to 12 meters, but it wasn't mentioned that we reduce its intensity. The intensity is still the same. Its new range, R sub 2. We're looking for P sub 2, power sub 2, given this new range, which is R sub 2 equal to 12 meters. So at range 1, this R sub 1, we have, and it is the same intensity delivered at range 2. So recall that if we write any equation of intensity, for example, I equals C epsilon naught E sub 0 squared over 2, there's no change in the electric field amplitude because it wasn't mentioned that there's a change in the amplitude of either electric field amplitude or magnetic field amplitude. So intensity actually still same. One of its usual definition is that intensity is the power delivered through an area of a system. So P over area. And since for both ranges, intensity remains the same, so I can write I sub 1 equals I sub 2. And plugging in the expression for intensity, we have power over area equals P sub 2 over A sub 2. We can assume that when the Wi-Fi unit delivers or emits electromagnetic wave, it's radially symmetric. It's like a giant wave, like something like this. So the surface area for this spherical wave is what? 4 pi r squared. So I can rewrite area here as the area of a spherical surface. So 4 pi r sub 1 squared equals P sub 2 over 4 pi R sub 2 squared. Cancel this out. Since we're looking for P sub 2, I'll just write this in terms of P sub 2. R sub 2 squared over R sub 1 squared times P sub 1. So plugging in the values, $16 milliwatts. Don't forget to like this video, subscribe to my YouTube channel, and hit the notification bell button for awesome updates. Thank you for watching.